this talk is some generalities, setting the groundwork like GNS construction and so on, and the kind of issues that occur already in finite dimensions with defining things like entropy. So I'll show examples. As was Lemani insisting, he gave me the story of a cat which was handled cleverly by Tenali Raman, which I won't do anything like that. Okay. Okay. So this is the second talk. I want to get into more technical matters, and it will deal with the Tomita-Takesaki theory, but in finite dimensions. Where does that whole theory come from? We can see it already in finite dimensions, and by matrix models, and I will show you how it works. The reason is that the third topic I want to pursue, and I don't know how far I will get, is to review a very remarkable paper, I would say, by Brunetti, Guido, and Longo, some time ago, which has quantized all positive energy representations of the Poincare group as classified by Wigner, all of them, massless, massive, all spins, including the so-called continuous spin representations of mass zero. He has quantized them. He has actually given these three people have actually constructed the Fock space for all these spins. We don't need any quantum field theory whatsoever to do this. And they show also things like how causality works. They derive the CPT theorem, spin and statistics. All these things are done entirely in the geometrical framework, in this framework, using this Tomita-Takesaki theory, but in infinite dimensions. Okay? So I will not do the infinite dimensional case. We can do it if there is interest, but the problem is that it involves certain technical issues. For example, when can you make a polar decomposition of an operator? In finite dimensions, we know the framework. In finite dimensions, any matrix, n by n matrix, has a polar decomposition. But in infinite dimensions, it has to be what is called a closed operator. Otherwise, it won't have a polar decomposition. Closed, densely defined operator. So I have to tell what that is. Why is that technique? Why is that point emphasized by these people? What is meant by a graph of an operator? Things of this kind, which I don't want to do because of time limitations. If there are particular topics I have already offered you, you can have separate sessions where we can try to understand these things together. That depends upon the audience. So here today, what I want to do is what I started last time. I was talking to you about the fact that in the, I shouldn't say modern approach, that will be like boasting, but the approach that is current amongst certain community, the primary objects from which we start are algebras of observables and density states of that algebra. So what is a state? I told you what is a state quite generally. The state is defined simply by saying algebra, I assume you know what it is. It is a vector space, or in this case, first it is a vector space over complex numbers. We can take linear combinations. And there is an additional operation in the algebraic structure, which is a product. Okay? The Lie algebra is a very special case where the product is not commutative. You take a commutator of the A, B. So if you write it in terms of standard products, it is AB minus BA. But in algebraic structure, an associative algebra, simply the product, like matrix products, are defined. Okay? And it is associative. And if you go into infinite dimensions, then you have to scratch your head and see what is the topology in which you come to make sure that what are the convergence sequences, what are the Cauchy sequences, things of this kind. at some point, if you go into it, you will be hit by these issues. For example, Ed Witten, just yesterday, there appeared a paper by Ed Witten, where he is trying to defend this earlier paper in DC space, and where he is worried about these issues. Because if you forget it, something goes wrong. Okay? So, so if you forget about it, an algebra is vector space in which an associative bilinear. So we are looking at associative algebras. So an associative, say product is defined, it is associative. That's it. Yeah. And we will mostly be pretending that all our algebras are finite dimensional, but this is not exactly correct. The quantum mechanical algebra is one of these things where this is not the case. So what we are given is a state which is a positive linear functional. What do we mean by positive linear functional? It is given here. First, it is positive means the algebra is given to you, but there is an additional operation on the algebra which is not, which is star. They call it a star operation. Okay. Star is, you can think of the star as an intrinsic an operation without a Hilbert space, which stands for permission adjoins, but that is you intrinsically define it. So it is anti-linear involution. That's what they will say. So star operation, and if you have complex numbers, you take linear combinations, you take complex conjugations for the coefficients. Okay. So it is an anti-linear involution. That is how they stated alpha star. So if alpha is an element of A, you know what is alpha star. And positive means that the state omega on alpha star alpha is positive. Okay. It's non-negative, I should say. So, a state omega on a is positive definite means omega on alpha star alpha is non-negative. And it should be normalized, which means that omega on the, so these algebras we are dealing with has something called the operate unity. For example, matrix algebras means you have n cross n matrices, and then there is a unit matrix in that algebra. And so if you multiply anything by that, you don't change it. Okay. You can also think of algebras where this unit is not there. Okay. For example, take all upper triangular matrices with diagonal 0. That is an algebra. Okay. You can take products, and those matrices will stay the same, but there's no unity. So I don't want to consider those algebras, although they occur quite naturally by people who are involved in, say, modular functions and so on. That comes naturally, but we don't want to consider them. Okay. So these algebras have a unity, and omega on unity must be 1. The real number 1. The reason is that omega is like a probability. This is the data. Yeah. So, but if you are given this data, we want to construct, we want to see how to recover our Hilbert space formulation. And I'll show you, I reviewed last time how to do this. Okay. By theorems in the literature, it is the case that any state omega acting on alpha can be written as a trace of density matrix times alpha. So very often I write omega at alpha as trace of rho alpha in finite dimensions. You can prove it. Okay. Not too difficult to prove this, and in my next lecture I will actually prove it. Yeah.
Correct. View the omega as the expectation value, the usual expectation value that we have.
It will eventually emerge like that after I construct the Hilbert space. Okay. But now I have no Hilbert space. I'm just given omega and alpha, and I want to see what is the Hilbert space, where I can write this omega as omega on alpha as the expectation value of alpha is some vector in the Hilbert space. But as of now, I have no Hilbert space. Okay. So
here you define some abstract quantity, but eventually maps to the expectation.
That is the whole point of GNS construction, that the Hilbert space is an emergent object. It is not there in the beginning. It emerges from the, Sebastian was asking, what is the, somebody else was asking, can I do everything I do here using Hilbert spaces? I think I have a good answer for that also, but we'll come to that in a minute. So what do I do? Last time I did it. So last time I showed you how this construction is done by GNS, is Gelfand, and some years later by Ibn Siegel, who was I think in MIT. Like, all these people were mathematicians, but they were deeply interested in physics, okay? And especially the epistemology of physics. Right? So, one way or another, so Siegel was developing the ideas of Gelfand. So there's some history. Okay? Neumann was looking at group algebras. There's something called, I see some professional mathematician sitting in the audience. He is there. Okay? So Neumann was interested in group algebras, and Gelfand, of course, he did so many things. Okay? So they got together and so Gelfand showed also he was interested in physics. So Gelfand showed how algebras were related to topological spaces. Okay? That was his basic work. Okay? And from there started this whole game of how to recover space-time from algebras, okay? Which even now is an ongoing project by people like Alan Kohn, Matilde Marconi, several others. So let me go on. So what am I doing? I take this algebra, which is some elements alpha. So I artificially associate, I associate to every element alpha of a Keck vector, which I call alpha, with a Keck symbol. I just write that Keck symbol, and the addition. So if I take alpha plus beta in A, then I will say that the omega of alpha plus beta is omega this. A of alpha plus beta, this Keck of alpha plus beta will be Keck of alpha plus Keck of beta. And this is a vector, so it becomes a vector space for complex numbers because A has that property. Okay? So this I can always do. Okay? If one is familiar with, say, finite dimensional group theory, the regular representation of a group is how it is done for finite dimensional representations for a regular representation of a group. And there is a similar construction for compact Lie groups. So compact Lie groups also start from this premise. Okay? So that's what I am doing here, nothing great, very fancy. There is some background in, say, finite group theory. But this is a vector space. I need I'm after a scalar product. What do? I define a scalar product using the data that omega is given to me. Okay? So I will say that the scalar product of alpha with beta is omega acting on alpha star beta. I state it like that. Okay? This is okay because alpha, if I put an equation like this, I need to make sure that the scalar product of alpha with alpha is non-negative. So I need omega of alpha star alpha to be non-negative. But that is one of the data that I was given right in the beginning. Okay. There is one of the data I was given right at the beginning. So I'm doing nothing inconsistent by saying that the scalar product of alpha with beta is omega of alpha star beta. It is a nice exercise. Can you point us? I can use this. Either. Okay. I can also hit somebody. They ask inconvenient question. Okay. All right. Okay. So this is it is a good exercise to go home and check that this equation already defines for you the Cauchy-Schwarz inequality. Okay? Just from this data, you can show that these lectures, the Cauchy-Schwarz inequality that you are familiar with finding the uncertainty principle can already be derived from here by some minor manipulations. You don't need a this is what is crucial for that equation. Okay. The only catch in this thing, which will be a passing remark here, but which can be important in some finite dimensional calculations, that by defining like thing like this, there could exist vectors there which are zero. So there may be vectors in the original algebra and in the original algebra A such that so I might have a sector vector n in A such that I might have a non-zero vector in A n, but the scalar product of A may be zero in the equation. So these are the null space, the null vectors for this omega. Okay. these null vectors are nuisance. Okay. Well, they happen in many places. Okay. I'll show you examples where this happens. So we don't like that because then it won't be a Hilbert space. Because the scalar product on a Hilbert space, the only vector non-zero is a zero vector of the space. Okay. That is not the case here. Need not be the case here. So we want to take it out. So take all these vectors n, which are of zero norm. One proves that the zero norm vectors already form a subalgebra. So take product of if you are familiar with BRST, the BRST cohomology, you have all these vectors annihilated by Q, the operator Q. And issue arises immediately, do they form can I multiply them? And you can, because of the fact that this null space of an operator like this, but
takes as a algebra, right? So alpha star beta is the first equation.
this one,
That is the alpha star beta is the element of the algebra.
yes.
So can you remind me how the ket alpha is related to the alpha element of the algebra? Right?
The ket alpha is only as a, so I take these kets, okay, and I say that what I want to define is not to put it here. I want to tell what is the scalar product of two of these kets. So the kets here will be replacing your wave function. Okay. So I'm going to say that the scalar product of two wave functions is given by this equation. I'm given omega, so I can calculate this. That is right hand side. So I call that as a scalar product. Okay.
Could I not have ket? Then we got alpha star beta.
Alpha star beta is another ket, yes.
How is that related?
You can prove that alpha star beta, if you take that case, that also has zero norm. Okay. If it is a case that beta has zero norm, you can prove that by short inequality. So, Cauchy-Schwarz inequality. So, the sector vectors which have zero norm will form by them. So, the vectors are labeled by elements of the algebra. Okay. Take those vectors which are given the zero norms. They are coming from some algebra elements and they form themselves a subalgebra. Okay. So technically they also form a left ideal. But let me carry on, and if there is interest, I'll show you how to do that. Okay. Then what do? What Gelfand did, Gelfand and Neumann did, was to portion these things out as one does when, if you are familiar with game theories, there is this BRST or BV formulations. Batalin-Minkowski homology. So you portion it out. You take this algebra and for the labeling of the states, I don't use the full algebra. I take A plus the equivalent class. So it portions it out of the null vectors. So now I will call a vector alpha tilde as small alpha plus all the null vectors. So this is not a single thing. This is a set in the algebra. This object is a set in the algebra. Alpha is one element, and it is belonging to some equivalent of the vectors composed of alpha and all the null vectors. To take any two vectors here and their difference, that's a null vector, because the alpha will be common. Then I say, so I define the scalar product by labeling the states with this tilde objects. Then you say alpha, and I will tell you what is the scalar product of alpha tilde with beta tilde. Take any vector from alpha tilde, anyone. Take any vector from beta tilde, anyone. So that will be some alpha and beta, and define the scalar product as omega of alpha star beta. Okay. And it doesn't depend upon what element you pick from this equivalence class. Again, that comes quite easily from Cauchy-Schwarz inequality, and I suggest that you try it if you are interested. This kind of thing will come later on in our calculations as well. These are called trivial consequences of Cauchy-Schwarz, and the fact that these ends, we just multiply them by any operator, don't change. Okay. It will be still n. So you might want to check that. It's quite easy. And I suggest that you do try it. as a practice to see whether I get. Now the question is, yeah,
Earlier, like of alpha stays of Bohr. So somehow omega had content of the Bohr. That is not appearing here. So omega of some gamma is some inner product which has no information about any Bohr.
I'll get the pro. You want me to get the pro? I'll get it in a minute. Yeah. Once I get the Hilbert space, you will know immediately what is rho is. Okay? Anyone will know. Okay? Once I have the Hilbert space. So the question is how do I get it? So but I want to see first whether this space I have constructed with tilde equivalence classes. By the way, again, some of you would have studied J series, the Fateh Popov goes and so on. And what is happening in all those cases are vectors with the equivalence classes. Okay. So any two things that case related define one vector. In all those populations, the Fateh Popov may be BRSP, the Patharville cohesivity, that is what is happening. So now I say that I now want a representation of these operators, like position operator acting on a vector. Okay. What do? I take a vector like beta tilde, and I say I take an alpha from the algebra, which is not in the equivalence class. Take one particular alpha, and I say alpha acting on beta tilde. I do it the following thing. I take any vector beta from this equivalence class, take this alpha multiplied, then find the equivalence class containing alpha times beta. That is an invariant definition of this action. That is, beta tilde is a whole set. Pick any one, multiply by alpha, and find the new equivalence class of this product. Call this alpha beta tilde. That doesn't depend upon what beta you choose. So this is a well-defined action of alpha on this vector space. So I have a representation of this operator on the H omega, which is a proper scalar product, because it has no null vectors. I mean, it has no spurious null vectors because I have taken out the null vectors. So this is a representation of alpha on a Hilbert space. In finite dimensions, this is in fact in Hilbert space. In infinite dimensions, you have to do one more thing, which I will not talk about, because you have to take complete it in the scalar product you are given. Okay? So you need the convergence of coefficient sequences, but that is also already the case in quantum mechanics. Functions of x do not form a Hilbert space. You have to complete them in the scalar product, and that will produce for you the Lebesgue square integrable functions and all kinds of junk. Okay? But unfortunately, you have to do it. You want a spectral theory, you have to do it. So, same activity you have to do in case you get into that degree of sophistication. So, now I have got for you a Hilbert space from the original data. I think. Yeah.
How we element of the algebra alpha, how do we get gets in alpha? Is that
It's just a label.
but all the vectors in addition to define a well-defined product in a production, we have to model this.
Okay. Now comes. Okay. Now, what is the original Keck vector? Okay. You wanted to know how do I write rho in this space? Okay. I'll give you. I did not write it yet. I'll tell you what you do. You take this alpha, take the unit operator in the algebra A. Okay. Take one. The algebra has one. Take the equivalence class containing one. So it will be labeled by one plus all these null vectors. Okay. It is so take the density matrix. So it is a Keck vector. So you compute the density matrix coming from 1 plus n. Call it rho. You can check that rho reproduces omega. the expectation values of omega is completely replaced, completely reproduced by equivalence class containing the identity. So the identity and this equivalent class is the null vectors is standing for your density matrix. So you can write out the density matrix also. I did not write it, but it will come occur to us again as we keep going, and especially as when we enter this Tomizaki theory, and also when we enter the quantization of all free spins. By the way, these are not marginal activities. For some reason or other, they are becoming center stage. Okay. Yesterday, as I was telling Nemani, there is a heavy paper by Ed Witten. It is full of this kind of stuff. Okay. He is very worried about what Marshall is called tube-like domains. Okay. And there is a domain of dependency, which becomes very important to understand what is happening in DC space. So he is worried about that. Okay. So quantization of all things. You have a whole community working on this with this Vassiliev equation. Okay. But for free fields, free case, it is done. I don't know why you want to write quantum fields. You can for free fields. It's certainly done by these people. Okay. They give you all the equations for free case. So what is the use of this writing field as a function of x? Okay. I'll come to that if there is time. Okay. It is not useless, but it is a subsidiary issue which can also be understood from this language. But I doubt that in the limited time I have, I don't know if we will have time. I know, yeah. It has actually been considered by Steve Weinberg in his volume 1. Okay. Why the Wigner representations from Wigner representations how to define fields and what is his role. He also shows, just to say, in that for volume 1, he already shows that gauge invariance is for free fields at least is Fourier. And it is not there. Wigner's classification has no gauge invariance. So how does it come? It comes from some properties of representations in the Lorentz group actually. And I think Steve Weinberg was the first person to understand this, and he gives all the details. And what use is it? You will see later. It turns out to be important to want to write causality. Otherwise, you don't. For interacting field, if you want to write interacting fields fulfilling causality, that you do need a field, which is a function of x and t, because causality is expressed in that language for interacting fields. So it comes back by some backdoor. So one can understand it also from the point of view of algebraic quantum theory. But I doubt I will have the time to do all this. So I want to. Sorry? Yeah, the vacuum state is simply a representation of the Fourier group, which is trivial. Yeah, that's it. Yeah. So you can take the vacuum itself as the vacuum defines a density matrix, and you can induce a representation of the entire algebra of Sorokas from that state, and that produces for you. That produces for you the entire Wigner representations as shown by Bruneti Gudo. So they start from the vacuum state. But the basic assumption you have a ground state, which is the vacuum state. Once you have given that, with canonical properties of Fourier group acts trivially on that, you can find all operators of the free field for any spin and any mass, 0, you can find it by starting from that density matrix by this construction. So that is what I want to do after I talk to you a little bit about Tomizaki, because that is necessary to understand what is happening. So somebody asked me, can you do all this using purely wave function? Every line I am writing here, you can write in terms of wave function. But what happens is, I'll come to that in a minute. A typical case where if you go on doing it, but sometimes you don't, for example, there's a classic original problem in finite dimensions of how to treat identical current. When I first came, I heard rumors that there is some problem with identical current in finite dimensional equation model. So you do lattice calculation, say n particles, you have troubles in treating identical particles, for example, fermions, because you have to anti-symmetrize the electrons. But everybody was checking, and you want to see how to define entropy. So suppose you have n fermions, and you want to see the entropy of, say, m or the inside that n. People were taking partial trace, and they were getting funny, absolutely meaningless result. For example, for two particles, in two particle case, they were getting an entropy which is always log 2. Always log 2. What is the log 2? Then there appeared papers which I only looked at. They are heavier than me by people like Girardi, who are working in race and some colleagues. 80 pages, 90 pages of papers. You see epistemology and all kinds of things. And I don't know what they are doing. But there's a new paper which clarifies something. I don't know what it is. He has not sent me the links. But in the algebraic approach, it is very clear what we have to do. And I can do it here, and somebody in a distance star can do the same calculation using the same answer. If there is no reason to use telephone lines to communicate information. So telephone lines are classical, and I don't know what that means. What do you mean by telephone information? I don't know what it means. But the rules are like he's smiling. Why? It's like there's a particular dish you take among community. Here also you get something called avian, where you put everything, or Irish stew, where you put every damn thing. You put a little bit of classical theory, a little bit of modern theory, mix it up, boil it. That is cannot be the reality. So, but this is what people do. They are doing at that time. And apparently still doing. Because they talk about that's an angle. Local operations in classical communication. Where is the classical communication? Where is it coming from? Who is classical? Maybe there is some mysterious understanding of what is the classical. I don't know. There's nothing classical in the world. But anyway, if Sibaji were here, he will defend him. But such kind of issues will not arise. You work with states in this library, and we looked at this issue and we got the answer quite easily. For us, the surprise was why nobody else did it. Quite obvious. So I'll come to that in a minute. So I want to give an example. Then we'll do a 2 by 2 matrix example. So the algebra is composed of all 2 by 2 matrices of this kind with complex entries. And a state which is labeled by a lambda. So I take a fixed lambda between 0 and 1, omitting 0 and 1. So each lambda gives me a state. And I define omega lambda on alpha to be this. I don't want lambda to do the 2 endpoints, because if I take endpoints, you start producing null vectors, and I'm trying to reduce my talk by not having to consider them. So I will take it away from 0 and 1. Then one can check that omega lambda on identity, which is 1 1 along the diagonal, is 1. Okay. Because I'm simply adding these two. And omega lambda alpha star alpha can calculate is non-negative, strictly non-negative. There are no null states. Okay. So it is quite easy to handle. Now what happens? The Hilbert space will be consisting of vectors of this kind. where the entries will be these 2 by 2 matrices. Okay. And the action of an operator beta, which is also a 2 by 2 matrix. Yeah. So the action of a operator beta on a vector alpha will be beta acting on that vector, the argument, and I can decompose it into 2 parts, one here and one here. Why do I do it? Beta acting on the first column, the second column 0, will remain like that under the action of beta, and likewise the second one. So the Hilbert space splits the direct sum of 1 omega 1 h omega 1, which is vectors of this kind, the second column 0, and vectors of this kind, which is second column, the first column 0. So it's a direct sum of 2 Hilbert spaces, both of them in 2 dimensions, and given by these equations. So I have 2 representations, which I will call phi omega. The representation phi omega of the operators is given by phi omega of 1 plus phi omega of 2. It's a direct sum of 2 irreducible representations. And in the case 1, the scalar product calculated by omega is there's a lambda there, and you get alpha 1 square plus alpha 2 1 square. This equation. Okay. In the second one, the normalization changes because the definition of omega had lambda and 1 minus lambda. Because of this, the normalization of vectors, the second column changes, you get 1 minus lambda times this object. Okay. So you get these 2 Hilbert spaces, and the scalar products of vectors are of this character. Okay. Okay. So this is an example of what one has to do to get the answers. And the case with null vectors, it is actually worked out in the papers I wrote with the people here, Govindarajan. Then 2 others, Amika Keros and Andres Yeager, some Bogota, he's from Colombia, from Bogota. We wrote a paper here where we have worked out more complicated examples of where there are null vectors, how to take them out and what happens. We worked it out completely, and it is in the net. It is doing some algebra and how to reduce representations of this algebra. But these are very trivial calculations. So I cannot say that we were tremendously proud of those papers. It is not. It doesn't merit what the Germans called Stumm and Drang. There is huge amount of noise. It doesn't merit that. It's just some routine things, provided you pay attention to what one is doing conceptually. There is no big deal there. Okay. Now I want to look at entropy. This again has come to center stage. In NBN matrices, so far as I don't understand, entropy is some subsidiary quantity. You measure other things like at least in quantum theory, you define entropy by finding out the density matrix and write minus trace rho log rho. But you have to find rho. How do I find rho? I do a lot of experiments to find out what the quantum state is, which gives the rho. So if I know rho, why am I writing entropy? What purpose is served by writing entropy in finite dimensions is not clear to me. Maybe it is useful to check about decoherence of vectors in quantum information theory, maybe, as it may give a measure of this decoherence. So it may be that, but it is a subsidiary object. It is not a fundamental object of the theory. But if you go to infinite dimensions, things start changing very rapidly, and we'll come to there. I'll mention what the kind of things that happens when you go to infinite dimensions. So let me see what the problem is. How would I define entropy in classical theory? That's very clear. The classical theory state is simply a probability distribution. And let us say we are dealing with phase space, you have the QLP, classical. So you take the U will measure rho QP dQdP and integrate your density matrix rho. Density matrix is your probability probability distribution or the classical theory, and we will define the entropy by this equation. We will take the logarithm of the function rho and integrate over the Liouville measure dq dv rho qb. Or if you are more sophisticated, you can use some more sophisticated definition of the state. Pick up Kolmogorov's original work, you see how to do that. You can do that also. Some sigma algebra, you can unleash a whole technology without loss of content, but a considerable elevation of tone. So other people will be greatly impressed by doing that. But you may not be doing anything more. Okay. Now, the problem with quantum theory is somewhat different. Okay. The problem in quantum theory is who told me that for a given state, there is only one density matrix. I showed you one density matrix which is given by the check vector, the vector state 1 of the identity of the algebra, corresponding check vector, gives you one density matrix. But who told me that there is only one? Can there be several others? Rho 1, rho 2, rho 3? Is that not possible? Where is the uniqueness theorem of finding a rho from omega? It happens that in fact this is not true. You can find several rows, density matrices, which are trace orthogonal. Some people will say should be trace of rho 1 times rho 2 should be 0. I'll show you how to find them. There are several of them. And to compute the density matrix in those cases, the entropies by trace of rho log rho, this formula, you get different answers. Okay. So what is it? What do I mean by entropy? Okay. In cases where the rows don't, you have several rows which are mutually orthogonal. I don't know what to do. Okay. Yeah.
Omega from A to real number, right?
Complex number. Yeah, complex number.
If there is a, so basically omega is the dual space of A, right?
It's a what?
A is a vector space. It has a dual space. So if omega lives in the dual space of A.
Yeah, omega is a dual. That's a good way to say.
If there is an isomorphism between these,
No, it is less than omega and rho. Omega and the Hilbert space may have duality. It's not. It's a cone. You see, the sector omegas do not form a vector space. Okay. So it's a dual space, surely. But actually, to get anything close to duality, you should remove the normalization. Omega 1 is 1. That I should remove. Okay.
but still, right? So it's a subset of the elements of the dual space.
Yes. And yes.
What I'm trying to say is that, so usually when you say you have a state, that's also a state. If we're talking about pure state, if there's an isomorphism, if I can say that for every element in A, there's a dual element in A dual, then for omega, I have a state cat omega. Then I can continue my things.
Except that this duality is for the vector space you are talking about. It's not one to one. There are many vector spaces which will give the same density matrix. That's what I'm trying to tell.
Okay, that would be the case. Then what I was using is not.
Yeah. So, for cultural value, I'll tell a problem which got solved only about 10 years ago. Okay. This problem was coming from, all of you know, Dirac's quantum mechanics. Dirac was the one who started this game. He said that in quantum mechanics, if pure quantum state can be labeled by diagonalizing a complete commutative set of operators, eigenvalues of a complete commutative set of operators. That is the premise from which one starts teaching quantum mechanics. So the complete commutative set of operators defines the corresponding rho, defines a state on the complete commutative set, which is an abelian algebra. That is the product of two operators is commutative. But the full algebra is quite big. Okay. It contains x's and p's and all kinds of things. This is a subset of and the commutative state is labeled in the state from a small set. Okay. So, but you can take, because everything is special, but I can take traces of all the operators and I get a number. Then it was raised long ago by Caddison and Singer. So this was the Caddison and Singer problem. They asked, this state of Dirac is given only on this complete community set. It's an abelian subalgebra. Does it extend uniquely as a pure set on the full algebra of operators? That was their problem. That they set that problem in, I think, sometime in the 50s or something. Okay. This is called the Caddison-Singer problem. It was not solved until the late, I think, 2000 something. Okay. It was not solved at all, and it was solved with the answer yes only in the late, I think, 2000 something by quantum information people. I get the impression that quantum information communities themselves is divided. Okay. There are these people who do quantum information with this LOCC, all those things. But there is another community which are very deeply into all kinds of math problems, including things like payment conjecture, this, that, all kinds of things. And they eventually proved, one of the people who proved it in that 4 people is somebody called Srivastava. And there were, I think he originates in IIT, but Kanpur IIT, but he's somewhere now in the US. And there are 3 other people. And the proof involved things certainly not at all obvious that, okay, just let me see. These algebras have a universal completion. Okay. It is called stone check compactification. Okay. So there is some way of compactification of the algebra of observables. This is called stone check compactification. It is some universal thing from which you can. Then these people proved that after do that, there are pure states on abelian algebras which are different from what Dirac gave in the full algebra. But they proved that the extension on this completion is unique. So one naturally asks, what are these states? What do you mean new states? You write it down. But the proof involves, of all things, the axiom of choice. So they say it involves the axiom of choice. And because it involves the axiom of choice, they cannot write it. Because if they write it, they would have proved the axiom of choice, but that is an independent axiom. You cannot prove it in this context. But it exists using the axiom of choice. And they prove it, they would, I think, have proved Riemann's zeta function conjecture, all kinds of things, so they cannot do it. So I'm telling this story because this problem gets, these are not trivial problems once you go deeper into the field. For example, there have appeared a few papers by a friend from Saha Institute, Kumar Gupta, Alex. A person has come out with a paper with a lattice model. He writes a Hamiltonian, okay? And he proves that you cannot find the ground state of that Hamiltonian. What do I mean? He proves that it cannot be done. Okay? If you put it in a machine, say a Turing machine, it will never stop. It will go on, 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 never stop. You cannot find it. Okay? I don't know what this means, but it is a maths proof of a Hamiltonian system involving all the operators which you are taught in class, normal things. So I would imagine that somebody who can program in a very wise way can get the answer. But what this guy says is, if you do that, your machine will break. I don't know what these things imply for quantum theory. Some new things are happening. For example, this written paper is also, some new things are happening, conceptually new things, and I don't know what they mean.
I think this algebra that we consider is some smaller subalgebra, which is abelian set, that would correspond to Dirac's passive commuting set. In which case, perhaps there's a dual space for which there's a one-to-one mapping, so that you can do the state mapping to the, and this state that you're trying to explain to the whole algebra. And these people,
Now, how to prove? How to prove it? Okay. The dual space is not electric space. Because the states or an algebra will come immediately to that. Do not form a vector. You cannot add two states with complex coefficients because the normalization will go disappear and it will not be possible to finish. Okay, they form a convex set. So that will be my next topic. So this is the problem. There are many density matrices with different values for this, but the state is the same. Trace the row 1, the algebra is trace the row 2 on the algebra. No expectation value changes. So what do I mean by saying what is the physical meaning of the row? Is it intrinsic meaning? And what does it mean by computing entropy? In this case, I don't know. I don't know how to interpret. Yeah.
so the secret. I can think of the entropy as
Oh,
but always comes from the same only.
but it's not unique. There are many. I only gave one example because somebody asked me. Okay. The natural thing is to take unity as a ket, compute the density matrix from unity, that will give the answer. But there are others. I'll show it you how to do that. And you'll get this Kolmogorov model for stochastic evolution of five-dimensional systems. This guy Kolmogorov was very clever. He had done five-dimensional irreversible systems already then. Okay. He wrote down equations for finite dimensions. Once he writes it, we know what he is talking about. Okay. They are irreversible. Evolution is irreversible. And these ambiguous things I am writing down, we will see are actually evolving by or given by some stochastic maps which Kolmogorov had considered. And because it is a stochastic map, they are irreversible. And all of them give the same eigenvalue trace. When you take the expectation value on an observable, nothing will change, except their entropy will go on increasing. So we will see that that will be okay. So I have to spend a few words on density matrices or states. What we know is that the states form what is called a convex set. What is a convex set? You take, say, alpha I are states. I can take combinations of these things with real coefficients lambda I, which are all non-negative, and who sums to 1. Okay. This is still alpha is still a state because the lambda is summing into 1 means to evaluate this on 1, alpha is 1. I get alpha I times lambda I times alpha I at 1. Okay. So alpha I are states. Okay. So when you add them up, alpha at 1, if you go out, I will get sum of lambda I 1, so I get 1. Okay. So alpha is a state, and it is because our lambdas are positive. Alpha of some positive element of the algebra will still be positive. So this is a state. So this forms a convex set. Do we know these convex sets? Yes. For example, if you do a simplex triangle. Okay. Triangle is a convex set. In fact, it's a simplex. The simplex is a convex set, and it is used in simplicial homology because it is a convex set. So what is it? You have this triangle, and if you take any point inside, it can be written as a linear combination of this point, that point. Okay. But you can write it uniquely in this case. So if I take any point here, it can be written as a linear combination of these 3 points today uniquely. So this convex set has 3 unique points which are called extremal points. The extremal points are those which you cannot decompose again into more elementary constituents in this fashion. So if I take the corner, I cannot write it as a linear combination of 2 other elements. So that is an extremal point. And in this case, the decomposition of any vector in terms of the extremal points is unique. But there is something else. Those who are doing quantum spin system, we know that the center states form the blocks here. Okay. The ball, it's a ball, and the extremal points are the surface of the ball, which is the two sphere. Okay. Here there are infinite number of it. So any point in the on the boundary, we know is a pure state. It corresponds to spin pointing in some particular direction. So I consider a spin half system where the center state is the ball, and any point here corresponds to the spin pointing in some particular way. And you cannot decompose them in other pure states. So the center points on the boundary are pure states, and you can write any point in the interior as a linear combination of points at the boundary. But here you can see it is not unique. Okay. But a point in the interior, I can write it as a combination of some point here and some point here, or some other 2 points. Okay. Which it can be orthogonal vectors. You can write it there. So if you take a point in the interior, this is the state. There are infinite number of ways of writing things at the boundary. And it is a simple exercise to check that they all have different entropes. So already we see trouble for one half spin half system. So this is a kind of trouble that comes. The extremal points. So there is a very important theorem by Krein and Millman, which says that if you give me a convex set, so convex set is defined by this equation. So it's a set of points where convex combination of the set is in the set. Convex combination is you say you can take linear combinations with positive real coefficients which add up to 1.
Let me take fancy. Still at the center of this class. How can I write it particular?
Maximally mixed
Half. Rho is half.
row with
Diagonal entries are half.
1 case.
The density matrix are half times the identity.
Density matrix is half, like that's a pure state. So at the boundary points cannot be written decomposed. So the extremal points cannot be extremal points are defined by those states which cannot be decomposed in this fashion.
It's not a this. Identity times half.
Identity is 4. 1. No, I don't understand.
Diagonal entries are half each.
Hmm.
Half diagonals are
2 half plus half.
Rho
Half.
half times identity.
Identity matrix, you write in terms of density matrix. What's the density matrix of 1? Oh, I see. You're writing the identity matrix is half plus minus half. Okay. That's what you're writing. Okay. The density, that's what you're writing. Half plus minus half. That is not a pure state. So
in terms of kids and not of kids. Just thinking of matrix, just a matrix. The diagonal entries are half
Yeah.
each. Half diagonals are each.
yes, I will show you. Okay, I understand. So you take the matrix with entries 1 along the diagonal, and you make it put a half in front so that trace is 1.
Okay.
Yes, that is not a pure state, and we will see how it gets decomposed into pure states in infinitely number of ways. Infinite number of ways in a minute. In this class, I will explain. Okay. That's not a pure state. Okay. So the Krein-Millman theorem says that any convex set, it's a technical thing. They say compact convex sets, but never mind. All our sets are compact. So the definition is you can take these combinations with coefficients adding up to 1. The theorem says, Krein-Millman theorem says that they always have extremal points. So that any state can be written as a convex combination of these extremal points. And the extremal points cannot be decomposed further. This is a Krein-Millman theorem, which is highly crucial also for people doing finite dimensional matrix algebras. Okay? But nowhere do they say that these are unique. The, it is not like a vector space, but so they look like these extremal points look like bases, but not really, because in the case of a basis, you take a vector and choose a basis, and you write it in terms of the basis. The expansions are unique by the basic theorems of. So any vector that you get by taking linear combinations of elements in the basis is always unique. You don't get two bases and get different vectors by adding them up. Here it will happen, but they will define the same state on the algebra because the fundamental object are not these density matrices. The fundamental objects are the omegas, and you'll get the same omega because the expectation values won't change. This is the issue, and I remember that having at that time I was not completely clear, having arguments with Bala and many others. How can this happen and so on? It happens. Now one can prove it. We were at the beginning of this game. Now one can prove it in many different ways, including things like the Tomita Takesaki stuff and many other things. So we will come to that in a minute. So the theorem that is said is that this kind of. So how do I define entropy? The canonical definition of entropy. So when you write trace rho log rho in terms of operators, there is already a problem. What do I mean by log rho? Rho is an operator. What do I mean by log rho? Well, if you want to mess around, you can write log rho as rho minus 1 plus 1 and do power series expansions in 1 minus rho. This looks like a poor man's substitute to get an answer. So, but there is algebraically there is a way to do this. You can write rho in terms of this spectral decomposition, in terms of projection operators and eigenvalues, and the way it is. So if the omega where rho, I can write an equation like this, where rho omega as density matrix, pure space, multiplied by some lambda. Okay? And what trace rho log rho means in fundamental calculation is you take lambda I and compute this is. This is also Channel's entropy. They are the same. So for the I can tell they are the same. Okay? By the same formula. And this is how it is defined. There is in the context of channel, this is how it is defined. In the context of polynomial, it's called functional calculus. You look at the spectral theory, you will see something called functional calculus, and this is the rule that is given there. And Dirac's book discusses it already in this book. Okay? What do I mean by functions of operators? It defines it by taking the coefficients of this expansion and taking the functions. These are real numbers or complex numbers, so they are well defined. Okay, so the question is this expansion unique? If it is not, I'll get different answers here. Okay. The answer is it is unique, even only if this omega is part of a simplex. So the theorem is that even only if the set of states I'm looking at is looking like a triangle or a simplex of higher dimension, triangle or subsequent 4 coordinates, 5 coordinates. So you have a simplicial decomposition of your space, then it is unique. It is not the case, and generally it is not the case. It is not unique, and that corresponds. Yeah.
So I are like I have problem with your lambda I want. So rho is the self-adjoint operator.
Yeah.
Then it has you can diagonalize. Take the eigenvalues and then you to the lambda I log lambda I. Then you get
a number.
What you have done here, you have defined lambda I with respect to certain pure state decomposition.
That is the same answer. I should say that omega I lambda, that expansion you're writing, the projection operators you're talking about, become this extreme state.
If they are projection operators of like all orthogonal projection operators, then
it will become this omega, the pure states define projection operators on one-dimensional subspaces. It happens in this case also. Okay.
Yeah,
So,
eventually that is if your state has to be something like that.
except that when there are degeneracies, you will find that you can write as so you might have several projections corresponding to projection operators on the same. So, the example I will give will be, for example, you have color. Suppose the quantum thing has color, okay? But I am looking at flavor. Okay? Then I write a state which is flavor diagram, but I don't know the color. I can change the color. Okay? Okay. There are 3 states in color corresponding to all expectation values in flavor being the same. Okay?
You're adding the tensor product of another input space.
Exactly. Exactly. That is exactly what happens canonically.
But if I diagonalize if I diagonalize the full sum, then I will get the answer.
You cannot sum because you don't know what those other operators are. You have no control. So what happens typically is the emergence of this is the power of, well, let me say it's true story. You have no control over that. For example, if you do group theory, let me go to group theory. If you open any book, okay, when they write down,
you're saying I'm given a limited part of profile.
that's all you have ever an access. That is the problem. Okay? For example, as I give you, take SU2. I want to find all its irreducible representations. What is a canonical way? You take functions of SU2. Now take functions of SU2, and on this SU2 acts on the left argument of the functions, and you reduce it, you find all irreducible representations by a canonical theorem. But there is another action which acts on the right of SU2 in the functions, which commutes to the left action. So what happens is that by a canonical theorem, each irreducible representation of SU2, say our dimension J, occurs 2J plus 1 times in this decomposition. Okay. 2J plus 1 time. You have no control over it. And the fact that you have a right action, you have no control. It happens. Okay. There's no way. So, in fact, a famous problem of Gelfand is to find quantum states where this does not happen generically for a group. So far as I know, it is an unsolved problem. Okay. So you have no control. Here it happens. How will I know? I say color, I cannot see color. Okay. But there's a degeneracy due to color for every quantum state I write down. I don't know. Here, what happens is that if the vector I'm starting from, in this case, the vector is this one vector, or in the Gelfand construction, suppose there are no null states. Okay. Suppose I can say, for example, in the example I gave you, I got 2 irreducible representations of the algebra. They're actually isomorphic. Why am I getting 2 instead of 1? That is because the vector I chose, the weight omega I chose had no null vectors. This will happen every time when you have no null vectors. And that is the heart of, to take the vacuum state in QED, QCD, whatever.
Now you're saying that I don't go. There
No.
may be some other degree that I have no access. So immediately the question, I can say that if you are getting multiple trophies or from 1 omega, that might correspond to the degree of freedom that I don't.
You can say that, but the problem is that we wrote papers, we call them as emergent symmetries because there is no way to avoid them. That's the problem. There is no, unless you, for example, take the vacuum state.
If I don't know exactly,
I'll tell you.
Yeah.
Tell me how. Take the vacuum state of QED or QCD. Take the vacuum state of QED. Okay. In a local algebra, so that is what people know. So take all the algebra operators in a local region. So in algebra, that's what AQFT they are deals with. There is, to act on this vacuum, okay, there is no vector in this local algebra which will annihilate the vacuum. That is because in the local algebra, there is no way to protect out the creation annihilation operators. For that, you need integration over all space. You can't do it because it's a local algebra. So what happens is this vacuum state I'm writing has no null vectors. So what happens? This local algebra, to find the representation of the local algebra, there's an enormous commutant, which will do degeneracies of the original algebra there. What is the physical meaning? This extra algebra is coming from causality. These are all the causal complements of this original algebra in this local region. Take that region, take the causal complement. There's also they will all come into this, but they can act on the vacuum. They change this, they give this ambiguity, and that creates a huge entropy. And the problem of resolving the entropy is a problem which has been tackled by different people in different ways. Now, again, Ed Victor has been come, and Longo and Chandrasekharan and one more person have been coming out with papers, and I see that Ed is again trying to defend that work by using some old work called Bockless. So there is no way to evaluate. This is the basis of this Tomita Takesaki duality, and there is no way to evaluate to get rid of it. So actually, I know of no way of getting rid of it. Some emergent gauge symmetry. It looks like an emergent somewhere out of nowhere. Some gauge symmetry arises. What is it? I don't know.
As far as I can see, that is the unique kind of
That the problem is that for the local algebras there is no density matrix. We are running far ahead. Okay? There is no operator in the local algebras which has a finite trace. So you cannot write a density matrix. Trace a row must be one, but there is no such row. This is coming from outside. Where is it coming from? If you like, that is the problem. Okay. There's one way to say all states and local algebras are mixed. There is no pure state. So what do I do? So I am claiming as we go that quantum fields are completely different in many of their characteristics than what we do in the finite dimensions. There are too many things happening which are a great surprise. I mean, people know just our intuition with messing around with quantum mechanics doesn't seem to work. So I will keep going. So it's already time, 3:15, I will stop. Okay. So this issue was brought up to me when we were doing this by Raphael, as usual. He has been doing some work along these lines for black hole entropy. So this issue was brought up when we developed it, and but basically his idea is so I come to that. I'll give examples using quarks, and probably because I'm going too slowly, on Friday I'll try to finish this, showing you the ambiguity, and jump directly to Tomita Takesaki. There are other things I can tell you, but we'll see. I do want to move into more technical issues. So I'll show this. This is very interesting because you see what Kolmogorov did to model stochastic processes in finite dimension. Extremely clever. You will see what he did here. Finite dimensional stochastic systems. I did not know about it until we encountered it this way. Then we'll go on to do other things. So, okay, I stop. It's already too late. Unless you have questions, I stop. There is a quotation. If you have read Coleridge's poetry, the Rhyme of the Ancient Mariner. Who has read the Rhyme of the Ancient Mariner? You have read it. There is a famous quotation. Okay? That is, one needs a willing suspension of disbelief. Okay? So when you hear all this, there should be a willing suspension of disbelief, okay? Because we are all brainwashed. But reality seems very different from brainwashed human beings that we are. So we'll keep going. Are there more questions? No. Okay.